All right, quiet please. First of all, questions on any of the homework. 1, 3, and 5, I think is what I assigned. Any questions on that? Betsy? Number 1? All right, for number 1, quiet please. I would, when I'm doing number 1, the cube root of 2 is in between the cube root of 1 and the cube root of 8. The reason I picked 8 is I know that answer is 2. I know this is 1. So the cube root of 2 is obviously between 1 and 2 somewhere, probably closer to 1. Just as an off-the-cuff guess, I would approximately guess that root to be 1.2. Now, when using Newton's method, we want to use it to find zeros of a polynomial. That was one of the things we did yesterday. So you have to take this approximation and turn it into a zero of a polynomial. Well, when x equals the cube root of 2 is your final answer, that means you probably took the cube root somewhere, so x cubed equals 2. X cubed minus 2 equals 0. So it's logical reasoning that says your equation, x cubed minus 2, looking for the x-intercept where it crosses the x-axis, would be at the cube root of 2. That gives you a function that you can take the value of and the derivative of. So you're looking for the zeros of the whole polynomial. In Newton's method, it says take your guess, your best guess, and run it through the function as your guess, and then also divide that by the derivative, and that should be your approximation that's closer. Now, I picked 1.2. Based on the graph, could you pick 1.3, 1.4? Sure, I guess. And then you just go to type that in like we did yesterday. I'm going to change that today, but we have one thing to talk about first. And I'll be the first to admit, I like to write programs just as much as the next person. In fact, I've, have written probably too many that I actually had to start erasing some. But today I'm going to talk about how to use a calculator a little bit more efficiently with Newton's method once you get the hang of what's happening. And it's not a program. So what I'm going to show you today would be allowed. Any programs that you have, I'd like to take a look at just to see how you're using them. But obviously you can't allow programs for your tests or exams or 10 for 10s. Yeah.
Why did you have to erase them?
Why? Because they were getting out, so to speak. When I was back in the day, we would link. We would use the links all the time between the calculators and use the programs and everything. Well, mine inadvertently got linked one time, and that had a little too much information on it, and it started getting out because scores started getting very high, with good reason. But that was one of the things, like I said, we had to do it for class. It was some fun programs. Yeah, it's actually pretty easy. All the triangle problems and the polynomials and things like that. So I'm going to take my guess, x, subtract the function value, which is x cubed caret 3 minus 2, divided by the derivative. I helped somebody this morning with this, or the other day, or yesterday or something. And I made the comment, I said, it's easier to type this in algebraically because it kind of helps you check your derivative to see if you're actually doing it correctly. And you press enter, you get 1.2626962. And then this is a nice feature, the auto store. Just hit store and it comes up again. And then the recall, second and enter, second and enter. Those of you going on, and I'm getting, you can see I'm getting better. I'm at 1 decimal place, getting ready to get 2 decimal places because it'd be 1.26. What did the directions say? Approximate to how many? 4. So I'd probably have to do it again. Store as x. Second and enter, second and enter. And so you end up with 1.259. So you'd stop there. You would cite those decimals so I could count the number of iterations that you did. So you'd cite those in your work, and that's how you'd answer the question. Okay? Thanks.
We just need to write out what we need to
No, your work should have somewhere, the derivative in it and things like that. So that would be in your work somewhere. Okay. No, I don't expect you to take a screenshot or write down every single time. Just a listing, and that will be changed after today, and you'll understand more about what I mean. Okay. Anything else? We talked about. No other questions on the homework right now. We'll answer more questions probably tomorrow. Yeah?
For the other ones, when it gives you an interval,
Sure.
is it best to just guess any number between, or is there a way that you can kind of make an educated guess?
I would just pick the number in between. I mean, between 1 and 2, I would guess 1.5.
Right, so
Mm-mm. No. And if you get too far away, I mean, you want to waste, like 2 minutes so you can go back and change your guess and start over. Well, I'm going to talk a little bit more about yesterday we talked about the linear approximation, and we talked about Newton's method. Correct? Newton's method was x sub 1 minus f of x sub 1 divided by f prime of x sub 1. And that gives me approximately x sub 2, right? Well, no, it actually does better than that. It's so close that we say it probably would be. When they were first coming up with these methods, I think, now correct me if I'm wrong, but that's how they used to, back in the day when mathematicians were writing programs very close to it, that's how they used to gauge the speed of computers, was they would calculate how long it would take to solve a problem. I'm not sure if that's still the case now, but I know pi was a popular way of seeing how fast you could get out so many decimals, and that was the speed of the computer at the time. My question is, are these two related in any way, since they're both approximations? They're both using the function, they're both using the derivative, they're both using an initial guess, and they're both coming up with an answer more refined than your guess. Is there any way at all that they're related? I don't know, let's find out. This is obviously Newton's method, and this is the linear approximation we used in the last chapter 2, I believe. I think I found it. If I multiply everything by the derivative of x1, this would be under a test question labeled show that. If you see the instructions or see the directions that say show that, that's kind of like the work you have. Like you have the question, you have the answer, and you fill in the in-between. Does that make sense? Show that, questions? Anyway, if I multiply everything by the derivative, I end up with x sub 2 times f prime of x1. I don't know if this is going to work. I just had this thought a few minutes ago when somebody walked in and I saw something on their notebook. I just wonder if they actually are related. x1 times f prime of x1 minus f of x1. Interesting.
Why are we doing that?
Well, they have to be related somehow, don't you think? They're both using the derivative. They're both using the functions. They're both using the x values. And this is a great question, should you ever come up with the directions show that. Newton's method is nothing more than a fancy application of your linear approximation used in chapter 2. I think it's great. Oh. Well, I've got the function value. Let's take let's take everything over to the other side, because up here I have a positive f of x sub 1, down here I have a negative 1. So it makes sense to move everything over to the left, doesn't it? Let's see, x sub 2 minus, oh, sorry. And after all, you should always be inquisitive when it comes to certain things. X sub 1 f prime. x sub 1 plus f of x sub 1 equals 0. Interesting, to say the least. I do have the derivative up here, f prime of x sub 1, don't I? On the same side, excellent. Oh, common terms, don't you see? Right here? Common terms. What can you do with common terms normally? You can, greatest common factor times x sub 2 minus x sub 1 plus f of x sub 1 equals 0. Interesting again. What is x sub 2 minus x sub 1? It's a change in x. Interesting. The prime of x sub 1, delta x plus f of x sub 1. Well, that's almost identical to the linear approximation. Some things are shifted around, some things are reused. How is it different than the linear approximation? It equals 0, and the other one equals the function value. Oh, I remember yesterday when I started to do this, and I said, let's approximate the square root of 7. And I started to take off with x squared minus 7. And we said, oh, no. You do f of x equals the square root of x. Remember that? This one you use if you're going to approximate a function value. How can this equal 0, though? What do you approximate with Newton's method? The roots of a polynomial. And what do you know about the roots of a polynomial? They cross the x-axis, and on the x-axis, y equals 0. So it actually is an offshoot, a very close relative, of the Newton's or the linear approximation, because those are the x-intercepts. So when you're looking for the zeros of the polynomial, you can take the linear approximation, move it around, and get some things. Or, we're going to get to the good part. Here we go. So when you're looking for it, so they are closely related. A little bit of algebra, a little bit of geometry, or not geometry, a little bit of algebra, a little bit of substitution, you got it. I think we'll do this one. Approximate the solution of x minus cosine of x equals 0. And don't forget, I mean, I do know what the calculator is capable of. Okay? Now I'm going to do this in a true, I first did this way back when I was doing my graduate work. F of x equals x minus cosine of x. Now I'm going to use Newton's method to approximate the zeros. So I need a derivative, correct? The derivative equals 1, derivative of negative cosine would be psi f plus sine. Okay? Calculator is obviously in radian mode, right? Who? You did that? Fantastic. Does anybody have any idea what radian value is equal to the cosine of the angle? Like what radian count? Like pi over 4. Pi over 4 is 3.14 divided by 4, so 3 divided by 4 around 0.75. What's the cosine of pi over 4? Square root of 2 over 2. What's the square root of 2? 1.4 divided by 2 is, so it's close, right? So pi over 4 is pretty close. I think I'll use that as a guess. That'll be my initial guess. Pi over 4. I'm getting this all ready because I haven't, the last time, I actually discovered this when I was working with Feigenbaum fractals for iterations. Yeah, it sounds really intimidating, but it's kind of like making pictures, mathematically pictures. I had to figure out a way to do it on the calculator. He used a Timex watch. I don't know, somebody look it up, see what they say about it on the internet and bring it in. Might be worth some points. The Feigenbaum fractals. Feigenbaum? Yeah, Feigenbaum. Okay? Anyway, this is where it came from. I was given this problem. So I'm going to use the iterations. on the calculator? Everybody in this room has done iterations. In fact, Jake Bach just did one right then. He pointed. You remember when you were playing the calculator games and you kept pressing enter and the numbers would change? And you see how high the numbers would go up? Bum, 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 bum. That's an iteration. Okay? So, I'm going to set the calculator up. You don't have to do it like this. But I'm going to set the calculator up for iterations. I'm going to use y sub 1 as my function, x minus cosine of x. I'm going to use y sub 2 as my derivative, 1 plus sine of x. Why am I writing it down like this? Well, remember, I'm supposed to write down everything, so Shane has a fighting chance of doing this. Yeah, obviously you have to be in radians. Just double check that. That's fine. Now, there are going to be more people writing programs. Like I said, I like programs, but unfortunately can't have any for the test. It's not my rules. It's the rules of the people that make the test. X minus cosine of x and 1 plus sine of x. If you're following along, great. If not, now's where things go a little quicker. Now that I have that in there, the whole idea is that cleans up the home screen. This is no longer on the home screen. On the home screen, I'm going to input my pi over 4, and then I'm going to press enter, and I'm going to get my decimal. Does that make sense? I'm going to put in pi over 4, I'm going to get my decimal. And we already know the decimal is around 0.75, don't we? I mean, it's not exactly. Yeah, whatever. Pi over 4. I'm happy with it. 0.78. Okay? So I have my decimal. The key thing I realized with these calculators was when I was doing the iteration, 0.785, was that is now uniquely stored in what variable of the calculator? The answer. And when the answer changes, the last calculation does what? It goes into the answer again, right? The last calculation is stored in the answer variable. Does that make sense? Great. So I'm going to take my calculator, and I'm going to say, look, I want you to take my answer, second answer. If we can't get recalls with people in this class, answer is going to be tough. It's above the negative, second negative. Answer minus, and we've done this last year, I know. This year, maybe we did or not. I'm going to go to seconds. Not seconds, sorry. On this calculator, it's just bars. Bars, y bars, function, y1. Parentheses, second, answer, close it. Okay? Does everybody remember this as function notation? So I'm taking my answer number, I'm running it through y1. I'm going to divide that by what? The function notation for y2. So vars, and some of you better write these buttons down. Y2, and parentheses, second, answer, enter. I was very excited when this actually did work. Because when I press enter, it ran my answer through Newton's method and gave me that. What happens when I hit enter again? It's taking this through that without recalling anything and giving you the next number in the sequence. Enter. And enter. Now, Mason, this is why I said it's going to make a little bit more sense. I want you to have your function, your derivative, and your list of values that you generated. Okay? Anyway, you get pretty quick the values. Pretty quick. I mean, Newton's method, which is an offshoot of the linear approximation we already learned, you get there pretty quick to the answer. So you can see when you type that seed into the math solver and the answer comes back like that, it doesn't take long to get there. Okay? Your calculator is a bunch of programs wired together. Yep.
So we can do it either way.
You can do it the way we did it yesterday, or you can do it the way we're doing it today. Okay? Well, it's cleaner. I don't know if it's quicker, but it's cleaner. And it's easier to see the change. Okay? All right. So far, so good? Now you can stop at any line you want. Remember, I can't stress this enough. This is your guess. Too many points have been lost in this question. I think it's an easy question. This is iteration number 1. This is number 2. This is number 3. Okay? So hopefully you understand how that is read on your notes. Okay? Or on your calculator. Yeah.
So we have to write down all 4 of those to all.
Well, it depends on the directions. I know on your test, I'm going to give you a guess. I'm going to ask you for your decimal answer on your second iteration. You will stop right here. Because if you go one more, look at the difference between the decimals from here to here and from here to here. There's no difference. So I couldn't tell if you were actually typing it in or if you just went to the solver and typed in pi over 4 and plus solve. I couldn't tell. But this way I can tell exactly what you're doing, and that's why I'm going to ask you for 2 iterations.
So if we were out things right.
Yeah. Just write it out. I mean, now it's, and the nice thing about this is, when you're doing Newton's method over and over for homework, the only thing now you have to change is your equations, your function and your derivative. So that's pretty nifty. Okay? All right, moving on. Here we go. Approximate to 4 decimal places. Square root of 57, compare the approximation from the calculator. Anyway, some of you need to understand that when you take this course, if this is not your last one, you might be doing Calculus 2 without a calculator. That's why I'm always bringing up the fact the square root of 57 is between what 2 square roots that you know? 49 and 64. Okay? So that would be 7 and 8. And yes, you do run these without a calculator. It's not that bad as you would think. So it's probably closer to, I don't know, 8 away, 7 away. So it's closer to, a 7.6 would be a good guess. Okay? The equation that would generate this is obviously x squared minus 57 equals f of x. Okay? X squared minus 57 equals f of x. So the derivative is pretty easy. It's going to be 2x. All right? Yeah, that's what I'm going to use is y1, y2. Mm-hmm. Oh, remember we talked about it? I said, when would x equal a cosine of x? We threw out pi over 4 because it's 45 degrees. So this takes the place of that a lot. So I'm just going to the calculator. X squared, Orrin, type it out, please. 57. Orrin Allen's in the house, right? No, he's been awake. He knows exactly what's going on. Mine like a steel trap. All right, this is the night. Well, I mean, it's not too bad. But anyway, I type in 7.6. I just press enter. And now I just scroll back. Second and enter. Second and enter. And I can reload and I can just press the enter times as many times as I want. There we go. Got down to 3 decimals. They actually are starting to use, in the last 2 years, they're actually starting to use these calculators in Calc 2 and using the 89s in Calc 3. Who? Yeah, you keep hitting enter as many times as you want. You can obviously do this with some other types of games and whatnot, but that's mainly the thing. Okay, what time is it? Nice. Excellent. 4 minutes? Oh, the brain break I did today, says I didn't like it, so I'm not sure if you guys will.
We'll love it. Is there a part of it?
No, it's not, but it's one in which people fell over.
Oh,
To
I like
4
that.
decimals, what's our final, where do we stop?
I would list all those as my answer. Okay? Because you have, this is the one that you list as your answer. That is your solution. Because it is the first number that gave you 4 decimal places of accuracies. This is the one you're checking it with. Okay? So that would be the answer. This is the one you're checking it with. And this was your guess.
What do you mean checking it for me?
Well, you see 7.55.
Similar?
Right, I hit it again, I got 7.549, so I knew that wasn't it. Then when I hit it again, I got to match all the way down to here. So this is the first place that happened 4 decimal places. You want your solution to be the first time it happens. Obviously, you keep hitting the calculator, to be done with. But, are you ready? I hope nobody falls over. Mason, come up here with me. You're always my brain break lieutenant.
Yes, sir.
All right, good. All right, go ahead and stand up. This one's going to be easy for Orrin. Alan? All right. It's going to be easy for it. Ready? I do? Oh, well, maybe Shane will do it. Ready? Take your hands, clap and miss, turn your thumbs over, interlock your fingers, roll your hands on through, and then take your head and rotate it clockwise. And move your shoulders as well. Clockwise, good, nice job. Now take your right leg over your left leg and continue doing so without falling over. Good. Now, while you're doing this, spell your first name backwards. Good. All right, now, take your right leg, place it back to where it was, and cross your left leg, and then take your head going the other direction, and your shoulders the opposite direction as well. And now say your last name backwards. No, did we already say it? No. We spelled it? Yeah. Now you're supposed to say your last name backwards. Last name. Yep. There you go. All right, nice job.
Nobody fell.
Well, actually they did. Mason Silver. Mason, have a seat. He asked permission. All right. Try this one. Okay? Try this one on your own, start to finish. Okay? This is only number 6, and they give you the interval. When they give you an interval, my numbers are off for number 6. That's number 4. Sorry. I'll just pick 2.5 and give it a guess. But go ahead and try to see if you can do this one from start to finish on your own, 4 decimal places. The equation's different? Yeah, I would put it's very interesting. This is just a mere offshoot of the linear approximation. Give it a go. She's probably the inventor of it. I'm writing Y1 and Y2, but if you're going to do it the other way, that's fine. Yes? This is the derivative, and this is the function. X caret. It said 4, I believe. Minus 5. Why am I putting up here? I'm just checking it. What?
Why'd you do 5x to the negative 1?
It's supposed to do 5x squared.
Yeah, I know. One was in the Y bars or whatever. So,
4x,
5.
3. All right. And then go up. What was it? Okay. Minus 5. All right. Second quit. Anybody do 2.5? Second, enter. Second, enter. Perfect. Anyway, this is obviously the guess. Number 1. Number 2. Looks like number 3, the third iteration, gives me my answer.
What would you want us to
First one.
You can stop right there. Okay? All right, how'd that go?
Wait a second. Last time.
Right. That time I went to the third one. Okay? Good. Let me check. I think there's one more I wanted to definitely do before we stopped. Was it 10? You want to do another trig one? Number. Yeah. When you're approximating the largest zero, there's only going to be, based on the Descartes rule of signs, there's only going to be one positive zero. And the possibilities are all the factors of 84. So, I don't know what you want to start with, but in this method, it doesn't take that long to figure out your guess is going to work, and you just go back and change it and start over. Yeah, you can look at the graph, but I don't know too many people want to take the time to look out at 84. You'd have to go from 0 to 84.
the thing where we go to poly and do that real quick then?
Well, you have that ability.
How do we do
You can. What?
How do you do it? Like, what are you supposed to do?
Well, I'll just graph it out and see if it crossed. Well, you're looking, the biggest it can be is 84. So I go y equals, clear, clear. And also, this way, I think you'll figure it out. When you do this, now you already have the function in to the y1 spot. So that's, and then I go window, 0 to, I don't know, I'd probably go to 50 first, just see what happens. If I need to go past that, oh, there's 7. So I know that's the only one. I know I don't have to go past 50 to 80. In my 126 class, when we do these problems, there are 3-digit numbers and 4-digit numbers. But right here, I know I don't have to go past, 50, so I know my answer's in here. So yeah, I'd probably pick something like 10 to start with. Okay?
Do we pick 7, what it is?
7, that's fine. And then you can use the use that to figure it out. Okay?
So it's
Right.
the same thing. It's the same thing we just did. It's
Right.
just a different.
Right. Yeah. You can still graph it out to find the guess. I think I was going to do another trig one. Oh, here we go. Let's do a trig one. And then we'll call it quits. We'll do this one. So we're up to 21 odd today. From 7 to 21 odd. We'll do this one. So the reason...
It's
Actually 20? Okay. So on 20, so is 21 still in this section? 19? Okay, so we'll do 7 through 19 on. Anyway, cosine of 2x, that double angle formula, remember there's 3 ways of writing it. I don't really need to do that. Oh, approximate the real roots of 2 decimal places. I would still go to the graph first. Y equals x squared minus cosine parentheses 2x. However, delete. Is there a domain on this in your textbook? Is there a restriction? Zoom 6 then. See, the nice thing about trig functions is you don't know how many roots there are going to be until you start looking. Oh, there we go.
So then what do you do with that?
Well, I would guess it's an even function, so I would guess -1 to start with. And I'd run it through there. So I guess -1. It's an even function because it's symmetrical to the y-axis. So whatever I get for a negative, the answer is going to be the same for a positive. Y equals, I already got it in there, the derivative, 2x. And this is where some of you are going to be stumped. You never have learned to take the derivative of this. Plus 2 sine 2x.
Oh, I did that right.
Excellent! Yeah, it's a feel-good moment. I like that. -1. Second, enter. Second, enter. Nice. The power of mathematics. Okay?
I don't understand how you choose which one to get, one or -1.
I said it's an even function, so it doesn't matter. I know all I have to do is now is remove the negatives and I get the same readout for 1.
After the one before you just looked at the single root.
Yeah.
What if there were more than one root? Two root.
Well, I knew from Descartes' rule of signs on 84 there's only one positive root. If there's more,
Oh,
right,
you want the large.
you run the biggest one. So I knew there wasn't one past that. Answer minus x.
So with this, your answer.
I use second and negative.
Yeah.
Why one part of the bar?
Yeah, you go to the bars. Some of you need to jot that down in your little note somewhere where that stuff is. Okay? That's good. Nice job. I'm done. Who?
For that problem, we have to do the same for,
No, it's
No, I would say it's an even function. Therefore, it'd be 1, 6, 2, 9, 1, 4, 4, 5. You know, it's an even function, so it's going to be the same readout. I'll probably just list this as my answer. I put plus or minus in front of it.